between 8 and 10 multiple choice to start the test. Then there would be between 2 and 4 short answers. The ones where you might have parts A and B and you have to describe theoretically what's happening. Somewhere between 2 and 4 of those kinds of questions. Then, for the mathematical portion, which you should answer to the nearest tenth, which a lot of you forgot to do last test, just to remind you again, it says it in the directions. You will be given 2 problems you must do, and then choose one of 2 for the last 2.
What are these called?
The mathematical ones, the third part. Okay, there's going to be 2 problems that you must do, and then I'm going to have you choose one of 2 of the last 2 problems to do. I'm not going to tell you the types of problems that fall into that category. You should be ready for all of them. So, let's go over some theory that I want you to know. Some theoretical stuff that might be useful for the first, 2 parts of the test. So, first, what does friction depend on? What does the force of friction depend on? Give me both answers, not just one. What does the force of friction depend on? Dirks?
Mu value and the normal force.
Yeah. The properties of the materials and the normal force felt, right? The normal force that's felt. We need to know what mu is, what FF is a function of. Now, what about mu?
Wait, you said the mu value of what?
The mu value and Fn. What about mu? What is mu a function of, Julia?
Material.
Materials only. Mu is a function of materials. Materials. Which is always bigger, mu s or mu k? Mu s is always bigger than mu k.
Wait, S is greater, mu s is greater than mu k?
Mu s is always greater than mu k. Why is mu s always greater than mu k? Cooper.
Because of the initial force needed to get something moving. It needs more for the static, but once it's moving, it's
Good. The initial force needed to get it moving is more than the force needed to keep it moving. Okay, that force needed to get it moving to break the static force is greater, okay, than the force needed to keep it moving. If you wanted to get into detail, it's because of those cohesive bonds that occur between the 2 surfaces. By the way, I've been using the word cohesion and adhesion, or cohesion I said. What is cohesion? What is adhesion?
the contact of the 2.
The T.
Not the contact of the 2. Close.
Bond?
Cohesion and adhesion are like, ever see,
Adhesive bandage.
yeah, if you see like an adhesive, something that sticks to something else, they're 2 different materials, it's like an electric force that is existing between any 2 given things. It may be so minuscule you don't notice it, but it's always there. Okay? What about the normal force? What are some things you can tell me about the normal force? Because we spent some time talking about the normal force at the beginning of the year. Where have we talked about it? And this is where you can definitely expect multiple choice kinds of problems about the normal force. What do we know about it? Give me something about the normal force.
How it's being pulled, how it's like opposing gravity.
Good. It opposes the weight usually. It usually opposes the weight. Usually, right? Usually it opposes the weight.
When is it not opposed to?
Well, how about this? Watch. If I were to hold this eraser on the board, the normal force is coming out of the board now. Ready? I'm pushing into the board, aren't I? Isn't the board pushing back? That's normal force, and it's coming out horizontally now. So it doesn't always oppose the weight. Okay? It opposes usually an unbalanced force that exerted on a surface. What else about the normal force do we know? There's a lot of stuff about the normal force.
Good.
Why is it called normal?
It's always there.
I explained this. Should have written it down. Use your notes maybe from 4-4. Why is it called the normal force?
Does the normal force change?
It does change. It changes on a lot of things, depending on the weight of the object, depending on the angle it's at, if there's an FP acting somewhere.
Is the normal force.
The normal force can only be figured out using equations of motion. You always have to use equations of motion. But again, why is it called normal? Why is the normal force called normal?
Using equations of motion.
Using like your x and y equations of motion.
You said it can only be applied to equations of motion?
Fn can only be figured out using the equation of motion. Depends on the scenario. Because Julia's question was, does it change? And my answer was yes, it depends on the situation. Nobody wrote down what I was told normal. I spent time talking about this. I talked about a building coming out of the ground, or a tree coming out of the ground. And I even held it like a pencil. There it is, Marco. It's perpendicular. The normal force is always perpendicular to the surface it's on.
So
The normal force is always perpendicular to the surface that it acts from or acts on.
How did that make it normal?
Yeah.
The word normal means perpendicular in two directions.
Oh, okay.
So the example I gave you was like a building. Every side of the building is perpendicular to the ground. So the building comes out of the earth, which is a plane, at a normal direction. Or it's called orthogonal, is another word, but it's a fancy word. Normal. Perpendicular in all directions. Okay? So if I had, I don't know, an object sitting on the table, the normal force acts straight up out of the table at a right angle. So it would act like this.
So that's why I always do that.
Okay, not like this. Not like this.
right angle.
Now, here's an inclined plane, and the object's sitting on the inclined plane. The normal force acts like this, ready? And this is where it gets different. The normal force would look like this, at an angle like that. Again, here's the plane at a right angle. You have to think about what a right angle is. Take a break. Come back. The normal force we've talked about so far is sometimes equal to the weight, sometimes equal to weight, right? Not always. The normal force is always perpendicular to the surface. That's why it's called the normal force. We solve for normal force mathematically always by looking at the y direction. The normal force always comes from the y direction. Always, always, always.
Whoa.
Okay? Sometimes the normal force, we have to use an expression, right? Sometimes we have to just use an equation for it and move it over to the x direction. Other times you can figure out the normal force. So it depends on the problem being asked. If the problem says find the normal force, then you can easily plug in mass and gravity and everything else. But if the problem says find mu, maybe you solve for the normal force in variables and then plug it into the x direction. Okay, so again, the normal force, we have to remember that we need to use the y direction to come up with the normal force itself. Okay? And on inclined planes, remember that although it's still acting perpendicularly, okay, on an inclined plane, it's acting at an angle now, right? The normal force. If I push into the wall like this, the wall is pushing back with a normal force that's now horizontal. Although obviously the normal force on this calculator is straight up and vertical, it's not that way when it's on an inclined plane. It's not that way when I'm pushing into the wall. So we have to consider the fact that the normal force can vary from problem to problem. The one thing we know about it, though, is that it's always perpendicular to the surface. That's the one thing that we really know.
And it's
Peter.
still always is in the y direction, right? Even on an inclined plane.
Yeah, even on inclined planes, because you're tilting the axis, it's still in the y direction, yeah. Mathematically, you're solving in the y direction, Peter. You should understand the idea of mu. As mu gets bigger, the surfaces have more chance of being like rough surfaces. As mu goes down, smaller mu's are smooth, frictionless surfaces. So ice would be a very low mu value. Or, say you're driving on the road and it starts to rain. That means mu goes down because it gets more slippery. So when you're driving and it's raining, you should be thinking to yourself, oh, mu is going lower right now. I got to slow down. I mean, physically that is what's happening. You can actually calculate mu based on the surfaces and add some sort of a fluid to that surface to see how it changes the friction force.
Wait, did we say mu s was a range?
Mu s can take on a range, well, Fs max can take on a range of values. That's what we talked about. I'll get to that in a second.
Okay.
Mu itself is the same number still, but Fs can take on a range. I'll explain that. Give me a sec, Jack. Remind me though if I don't get to it in this part. What are the three possible scenarios? Or what are the, I guess not three possible scenarios, what are the three things that are true when you're in a state of equilibrium? In a state of equilibrium, what are the three things that are true? Give me one. Constant velocity.
Whoa.
No acceleration.
Okay, or, be careful, there's possibilities. Listen, when you're in a state of equilibrium, there are three things for sure. Your velocity is either zero or constant. That's one thing.
There's no acceleration.
The first thing is that your velocity is either zero or it's constant, either one. The second thing, Julia,
Acceleration zero.
there's no acceleration. That's what kind of gives you the first thing, really, right? When there's no acceleration, you know there's either no velocity or the velocity is constant. What's the third thing that is true in a state of equilibrium? You have a balance of forces. Okay? Balance of forces. A good example of a state of equilibrium, think about two arm wrestlers. Think about two arm wrestlers that are stuck, and they can't, neither of them can beat each other. They're stuck there. That's a good example of a state of equilibrium. They're both applying forces that are equal and opposite of each other, so nothing's happening there. So state of equilibrium, the net force is zero, or forces are balanced. There's no acceleration because forces are balanced. That's why there's no acceleration. And as a result, velocity is either constant or zero. Okay, that's the third thing. In Lab 4, which you guys worked on the computer where you were pushing the refrigerator and you had to get it moving and stuff. A lot of you, I started grading your reaction today, I started looking at it. A lot of you are answering with good description. I like that. The idea behind it is that, remember, that when you push an object with a constant force, if there's no friction, that means that you're accelerating it. It's getting faster and faster and faster if you apply constant force. But if there is friction and you apply constant force, you might be just battling against that force of friction. So you might not be accelerating in that case. So it depends on the problem in the scenario. If there's no friction and you literally apply the tiniest force, it's going to cause motion. The object's going to accelerate and it's going to increase in velocity. And it will continue to increase over time. So if I simply just tapped an object, right, just pushed it, it might get it to move at 1 meter per second. And then I remove my hand from it. It's going to continue to move for 1 meter per second forever and ever and ever. That's inertia. Or the fact that there's no external force slowing it down, there's no friction pushing back. But if there's friction pushing back and you push something and then stop pushing it, it'll move, but then it'll slow down or it'll come to a rest eventually. And you saw that in the lab when you push the object and then you remove the force from it, it would continue to move forever if there was no friction. And it moved at a constant rate after that point. Okay, but if there was friction, it would slow down. It would slow down. Now, let's talk about static friction and the idea behind static force. If I have an object, Jack, this is your question you're asking. If I have an object and it's on a table, and I pull on the object with a force of 30 newtons, okay, I pull on the object with a force of 30 newtons, and it doesn't move, it doesn't budge. What's friction? 30 newtons. Well, let's discuss that, Jack. Hold on. So friction is always opposite the direction of motion. Because there's no motion here, the desired motion is to the right, so friction has to act to the left. Okay, remember friction always opposes either motion or the desired motion.
So is that negative 30 or negative 30?
Well, think about it.
No, he's asking what you drew. Is that...
No, I wrote 30.
Oh.
It just says 30. The equal sign kind of got carried over. Okay, so it just says 30 there. Now, in your equation though, right, Cooper? In the equation it would become Fp minus Ff because of the direction of the arrows. So the negative portion of friction is incorporated in the equation of motion. In the diagram, I know that friction is technically negative because the arrow is back, but I don't label it as negative 30. We've never done that. Right? So the idea here is this. If I then pull on the object with more than 30, with 40, and it's still not moving, so I change this, and I apply a force of 40 newtons, and it still isn't moving. Well, what's friction now? 40. Now friction is 40 newtons. Okay, it's still not moving. I try 50 newtons, and it's still not moving. What's friction now? So do you see how friction takes on a range of values when it's static? It depends on how much you're applying. Until what happens? Until it starts to move. Jeez. It's so difficult to yell over that.
Wait, so you said the force, not the force of friction.
So, friction, the force of friction will continue to increase. And I keep pulling on it with more and more force, it's still going to increase until I pull with enough force that it starts to move. That's Ff max. FFS max, or whatever you're looking at in the lab, the static maximum friction. So let's say, I see your hands, guys, I do, hold on. Let's say I increase this by intervals of 1, right? Let's say I get to 41, and it doesn't move. And then I change it, and I pull a little harder, and I make it 42. And at 42 newtons, the object begins to slide. At 42 newtons, that means that the maximum static friction force is just under 42 newtons. All right, so again, if it just begins to move when I push with 42 newtons, it means that 42 newtons was too much for friction. So friction has to be less than or equal to 42 newtons. It's just under 42 newtons.
But why equal? Like if it's equal, you wouldn't move the object.
I'm saying equal right now because, technically speaking, what if this was like 42.1? I'm not being precise, so I'm just saying that. But theoretically, Sarah, theoretically, it would be less than only. Okay, it would just be less than. But realistically, it might get up to 42, it might be 42 and change. I don't know how precise I am with my data. But if it's exactly 42 that gets it to move, then friction is less than 42, yes. Absolutely. It's a good point to point out, Sarah. I should have just used less than. Yeah.
So FP directly relates to
In this situation, yeah, absolutely. Well, I mean, it depends on the problem. If you have a problem where there's a force at an angle now, then it's FPX that's pushing against friction. If you have an inclined plane, then it's FGX that's against friction. So it depends on the scenario, but this is the easiest way to understand this concept. Okay? So if you have to explain how the force of friction that's static takes on a range of values, you should be able to do that in words. You should be able to explain what we were just talking about.
So would you say that it's changed just due to the force applied on the object?
Yeah, so the amount of static friction increases as the force pushed on it increases. Yeah, absolutely. Until that force exceeds the amount of static friction, and then you know the limit it's at.
The amount of friction increases as the amount of force increases?
Sure. Word however you like. All right. Hey, let's think about this. Ready? So, question for you. Let's say a rocket in space. Okay, there's a rocket in space and it's burning jet fuel out the back of it. Okay, so a rocket in space is burning jet fuel. It's following this trajectory. What happens when an object burns jet fuel or burns fuel? What happens to its overall mass? It decreases, right? The mass definitely decreases. It's like in your car. If your gas tank is not full, you have less mass. Obviously, it's very insignificant in the car, right? Now, with something like a rocket, the jet fuel takes up a good component of the mass. So as it burns jet fuel, the mass decreases dramatically. What does that mean? What does that mean? What happened to the acceleration of the object if the force being exerted was constant? If the force exerted by the rocket is not changing, but it's burning fuel and the mass is going down, what happens to its acceleration as a result?
Goes up.
Why?
because although the speed is constant, the mass is going down. So, it's kind of alright, an object with less mass might be given the same amount of force as an object with more mass.
You're absolutely right. Finish. Come on, you're right. Focus.
We'll go faster than it.
Yeah, that's exactly right. And Jack said right away, increases. Look at Newton's law. Take a look at Newton's law. If the force isn't changing, pick a number for force. 20. And let's say the mass was 10. What's the acceleration, everybody? 2, right? Because 2 times 10 is 20. Again, acceleration would be 2. Now, what if the force is 20 and the mass instead is only 5? Now, what's the acceleration? It's 4 now, right? So in this case, the acceleration was 2, and in this case, the acceleration was 4. So if you apply the same force, 20 newtons, but your mass goes down, the acceleration has got to go up, right? It only makes sense logically. It only makes sense logically. That's how we relate our force, mass, and acceleration. So that's how, you could consider the fact that you're still incorporating section 4.2 and 4.3 with F equals ma, although this is really, now in section 4.4. It's the same idea, the same concept. Hey, what do we know about mu values? They take on a range of values, but what do we know that they cannot be? Mu cannot be negative or greater than 1. I'm glad you guys both picked up on that. I don't think I've said that explicitly. We've alluded to it many times now, though. Mu can never be negative. It doesn't make sense. It's a material property. Like density cannot be negative. Okay, it's the amount of object or material in a certain given space. Mu is a material property. It's not negative. Secondly, mu can't be greater than 1. Okay, mu can't be greater than 1. It's always a range of values between 0 and 1 exclusively, not including those endpoints. Some of you did this and some of you did not for that extra credit. What does a scale measure and how does it actually work? You can give me some sample that did the extra credit. Peter.
Scale measures normal force.
Good. A scale measures normal force. Good.
So say like in our elevator, when the elevator stopped, normal force increased, which increased the weight, right as it was stopping.
On the way down, on the way up,
On the way down.
Yeah, on the way down, as the elevator begins to slow down, right? The elevator is moving down with a velocity that's negative, and then it starts to slow down, which means it needs to have a positive acceleration. So the ground is pushing back up on you, and you'll feel that. As the elevator hits the bottom or hits the ground, you'll feel it pushing back. So it changes the normal force. Okay, it increases the normal force, or it increases what the scale is reading. Okay, so a scale reads the normal force felt. What happens as I take an inclined plane and I increase the angle? This is a tough question. What causes this to actually start to slide down the ramp? What's physically happening?
Is there a decrease in friction?
No, not a decrease in friction. That's a good idea, though. Good idea. It's not a decrease in friction.
What was the question?
As I change the angle of an inclined plane, as it becomes more and more inclined, an object will eventually begin to slide. Why? Why? This is tough to understand. A free body diagram might be useful to help to see this. So let's see. If I wanted to see what's happening physically, let me demonstrate. Here's a slight incline with an object on it. We know that down the ramp is FGX, up the ramp is FF, out of the ramp is FN, into the ramp is FGY. Okay? As I change the angle theta, which of these four forces is a function of theta? Which of them involves theta?
FGX and FGY.
Yeah, FGX and FGY. Marco, what's FGX? Do you remember the formula? What's the formula for FGX?
mg cos theta minus 0, or 90 minus theta.
Yeah?
Can you get that out of the text?
No, you know that, here's what you have, first of all, look at your formula sheet. Second of all, this is what you're given, right? Look at the top right, Marco. This is what you're always given. That's on the formula sheet. So if you're looking at the x component, Marco, you're going to use cosine after the mg, but because it's on an inclined plane, you're using 90 minus theta. All right, so if you remember those pieces, you kind of are given it in this sense, but you're not really, okay, directly given it. And then this is mg sine of 90 minus theta. So here's what's physically happening. As I change the incline angle, so here's a flat surface, here's an incline, it's still not moving, and then eventually it starts to slide. It's kind of stuck in my hand. It starts to slide off. What's happening is you're increasing FGX. The part of the weight of the object that acts down the plane is increasing as theta gets bigger and bigger and bigger. And try it. So do me a favor real quick. Type in, take your calculators out real quick. As you increase the angle, you're increasing FGX. I'm going to explain it, so if you didn't get it, give me a minute and I'll explain it. Think about this. Make a chart in your mind of this. And if I have a ramp angle of 10 degrees, and then 20 degrees, and then maybe 30 degrees after that, I want to see what happens. Okay, what happens to the value of mg cosine 90? Assume mg is like 10 or something. It doesn't matter what mg is. Think about this as the number 10, okay? That's what mg is. It's 10. What happens as a result? Type them in your calculator. Please do it. It'll be a lot more obvious to figure it out yourself. So take 10 and multiply by the cosine of 80, right? 90 minus 10. Then take 10, multiply by the cosine of 90 minus 20. Then take 10, multiply by the cosine of 90 minus 30. Try these out and see what you get. Give me the numbers.
One of them was
Point what?
0.173,
Uh-huh.
0.342, and 90 minus 3 cosine.
Are you sure? Yeah, Cooper, I don't think those are right. Are you in radian mode or degree mode?
Why are you multiplying by next to me? Because your theta is. Oh, that's what I did.
Again, assume the weight of the object is 10 newtons up here. So replace mg with 10 and multiply by the cosine of 90 minus theta, where theta is changing. Victoria, what did you get for the first one?
1.73.
Did others get 1.73?
Yes.
Next one, Victoria?
3.42.
And then?
5.
What? So what happens to FGX? What do you notice as the angle increases? FGX gets bigger and bigger and bigger. So as I take this angle of the plane and do this, more of it is acting down the plane. So it's increasing FGX, the component of the force that's parallel to the plane. It's getting bigger and bigger and bigger until you reach this angle at which it slides down. It overcomes friction that's acting up the ramp.
Know what MG is.
I gave it to you. I said, assume the weight is 10. Let's give it. Multiply by 10 each time. I was saying, assume that this quantity, the mass times gravity, was just 10 newtons. Okay?
Oh, yeah. You're really elegant.
Remember, anything from 4.1, 4.2, and 4.3 is fair game. So I recommend just looking through your theories in those notes, because they come up in these problems.
And multiple choice
Okay.
or a short answer.
Anything, anyway. All right, so
Could you scroll a little bit? Oh, okay.
there's a lot going on this slide. So Jupiter, the planet Jupiter, has a bigger gravitational field than Earth because it's more massive.
Yeah.
It's more massive. So what does that mean?
There's a greater
Gravitational pull.
What does it mean?
Gravitational pull is.
Yeah, you would weigh more on that planet.
Which means more Fn, which means more friction.
Absolutely. All those are correct. Very good, Marco. That's good. See, he's extrapolating that idea.
Can we say that a little slower?
He's making the connections.
What does that have to do with it?
Jupiter.
Okay? So if there's more gravitational force, it's because there's a higher gravitational field. On the moon, you only weigh, what is it, like a sixth of your weight? It's because G is a smaller number. It's not 9.81. It's like 1.6. On Jupiter, it's like 22.5. Okay, that's why you tried those different problems in your lab where you changed the settings. So you understand the idea. Now, let's make one quick distinction, because I noticed this mistake. On some of your homeworks, I've noticed this. The amount of mass of an object is different than its weight. So if a problem begins by saying this, the weight of an object is 35 newtons. What is that? Variably. What variable is 35 newtons?
FG.
Fg. Again, let's write this down, because I've been noticing this over and over. Come on, load. All right. If you're told in the problem that an object has a weight of 25 newtons, and then whatever else the problem says, that means right off the bat that Fg is 25 newtons. You don't need to multiply by 9.81 when you already have the weight. Many of you use this as a mass and then multiply by 9.81. If you needed to get the mass, you should remember this formula. Okay, which is like your most basic formula for this section so far. Fg equals mg. If you needed the mass and you have the weight, take the weight and plug it in right there. And then solve for the mass. Say a problem gave you the weight, but you needed the mass somewhere in the problem. You've given a weight. Plug that in for Fg, because that's what Fg is. You know gravity on Earth is 9.81, and you can find the mass. So the easy thing I remember is this. You can jot this statement down if it helps you. If you're given the mass, multiply by 9.81 to get the weight. You're given the mass. If you're given the mass, multiply by 9.81 to get the weight. If you're given the weight, such as right here, divide by 9.81 to get the mass. Again, if a problem gives you the mass, then sure, take mass times gravity, you have the weight of the object. But in any of these problems where you're given the weight of the object, you already have Fg. There's no need to multiply by 9.81. Okay? Key and then Summer.
So will the weight always be in newtons and the mass will always be in
Absolutely. Absolutely. Yep. That's another reason. Like, if you're given anything in newtons, it can't be the mass. If you're given something about an object in newtons, it's most likely its weight.
Yeah, the weight can't be kilograms.
And the weight cannot be kilograms. The weight is always newtons. The mass is always kilograms. Summer?
You were saying more gravitational force means more.
When, just now or before? Means a higher gravitational field. So if the weight of an object weighs more on a planet, it means that planet's G value is bigger than Earth's.
So you divide 25 newtons by 9.81?
To get the mass.
2.5.
Okay, again, please keep that in mind.
So if you're given the weight, you have FG?
You already have Fg, absolutely.
I'm sorry, so just one more time. If there's more gravitational force on another planet, which is why you weigh more?
If there's more gravitational force on the planet, it means that the G value on that planet is bigger.
Okay, what were you saying about weight and you weigh more?
You will weigh more on another planet.
That's what I told her. If there's more gravitational force on the planet, the gravitational field is stronger. That little G is bigger. I suggest, for the mathematical parts of this test, I highly suggest you do two things. One, study the stuff you've done already. Study your examples from in class. Study your problem set solutions that you did, or study anything you did in the lab. The second thing I suggest you might do, I'm going to put up a sample of like just 10 questions. Just like sample questions you can look at. Please do not email me tonight asking for every single answer of every single question on there. I'm also going to put up the answer key for it, so you can just look. Is that clear? So I'm going to put up like 10 sample questions that I also worked out and solved myself, so you can see the answers to them if it helps you to practice tonight. But if you can do the examples that we did in class, you should easily be able to do the stuff we do on the test. Is that clear? You should easily be able to do the stuff we did on the test. But please study the examples we do in class. They're there for that reason. Look at your homework examples. Let's do an example of something that's pulled at an angle. We just did in the last period something with an inclined plane. Let's go to an angle now. 125?
Yeah.
125?
Yeah.
Okay, 15 minutes, perfect, all right. So let's say we have an object. That's pulled at an angle of 23 degrees below the horizontal. If the acceleration of the object is 1.4 meters per second, and let's see, the force applied is, let's say, 60 newtons. The acceleration of the object is 1.4 meters per second, squared. And the force applied is 60 newtons. We also need the mass of the object to be given. I'm going to have a run-on sentence. I know. Let's just put a comma there. And the mass is 8 kilograms. Determine the coefficient of friction. An object is pulled at an angle of 23 degrees below the horizontal. If the acceleration of the object is 1.4 meters per second squared, the force applied is 60 newtons, and the mass is 8 kilograms, determine the coefficient of friction.
Is that moving?
I don't know. Is it UK? Is it US? What is it?
UK.
Why?
No.
US.
Why?
No, it's UK because it's
Why? It's UK because of acceleration. Guys, remember, K means kinetic. Kinetic means motion. Acceleration means motion. Even if it was moving, if it had a constant velocity, it would then be US. Keep that in mind. Okay, if I said this object was moving with a constant velocity, you would say, okay, well then acceleration is 0. Okay, so then really constant velocity, it's like you're looking from US. It's the same thing US and UK in that problem. It's the exact same equation. So let's take a look at a free body diagram of this. It's pulled at an angle of 23 degrees below the horizontal. Below the horizontal.
Theta is negative 30. Or 23. I don't know.
Yeah, theta is going to be something funky here, right? I wouldn't say negative 23. What I would do is I would just draw it differently on the diagram instead. So here's the horizontal. Let's draw the horizontal. Okay, there's the horizontal. Why am I putting it there? Because my pull is always on the top of the object. I always put. Okay, there's the horizontal. Now, it's being pulled at an angle of 23 degrees below the horizontal. So you start at the horizontal, and you draw an angle in. That's like right here. That's 23 degrees below the horizontal. So your FP in this problem actually looks like this. And I did this just to mess with you, okay? To show you that it doesn't matter whether it's above or below the horizontal. It's how you draw it in the diagram that matters. So if this problem said it was pulled at an angle of 23 degrees above the horizontal, FP instead of being acting down would be acting up at an angle like that. Okay, again, if it had been 23 degrees above the horizontal, the line would be up here right now. What does this do to the problem? The only thing that it changes is this. FPX is still to the right, but FPY is now down, negative. If it was up like this, then you'd have FPX positive and FPY also positive. But the components of FP look like this in this diagram now. This is FPX. And this is FPY. That's how I break up FP into its components in this problem. I break it down by saying, well, here's a good example, ready? Have you ever seen those strongest man competitions?
Yeah.
Or strongest woman or man, whatever it's called. If a person has to pull, ever see where they like pull a tractor trailer, where they have like a rope that they bite down on and they pull the whole truck? Ever seen this before?
Yeah.
Bless you. The rope is usually attached at an angle to the top of the truck. So that's an example of this right here. Imagine this is like a super strong person has the rope, he or she's biting down on it, and they're pulling one step at a time. The angle of the rope is like this. Okay, so that's this right here. Here's the person pulling on this big truck. Alright? Now, if that is true, bless you. If that is true, what's acting against motion? Friction. Always pulling down and always pushing back up. All right, there's my free body diagram for this. Now, once you write in FPX and FPY, you can simply cross this FP out. Okay, because you've taken FP and you've broken it into pieces. The pieces that matter. Okay, we can take this and get rid of it. It makes it so that everything is either horizontal or vertical now. That's why we do that again. Remember, when anything is at an angle, we really want it to be parallel to either the x-axis or the y-axis. So I break it into its pieces. Andrew?
So FFK is the same thing as like FK, right?
Sure, the book uses FK, I think, right?
So what?
Yeah, so FFK is the same thing as that, yep. All right. My given information so far. I know the acceleration is 1.4 meters per second squared. I know FP is 60 newtons. I know theta is 23 degrees. I know the mass is 8 kilograms. That's the information I'm given. Okay, so that's what I should have written so far. We were given acceleration, FP, theta, and m. What was our goal to figure out? Mu k. Mu k. That's the goal. So, equations of motion are the same in every single problem. It says sum of the forces equals ma. And then from there you analyze the problem. So we look and we say we have two directions. In the x direction, sum of the forces in the x equals ma. In the y direction, sum of the forces in the y, in this case, equals 0, because there is no a in the y direction. There's no acceleration. Remember, this acceleration up here is really ax. In the x direction, what is acting on this object in the x direction? Marco.
Is it Fn minus Fg?
X direction, Marco.
Oh, FFK minus negative FFK plus FPX.
Very good, Marco. Again, if you can draw a free body diagram, it takes, 2 units of brain power to actually write this equation here. I'm trying to emphasize the fact that this is not difficult. All you're literally doing is going up to the diagram. You're looking at the negative arrows, making those negative, and the positive arrows, making those positive. Okay, that's all you're going to do. It's the same approach for every single problem. Just go back to your free body diagram and analyze it. There's only 2 forces acting in the x direction. That's them right there. Andrew.
So first thing is why are you why are you solving for n a so what is that?
I'm not solving for it.
Okay.
Why are we setting the equation equal to ma?
Yeah.
Because there's acceleration, and Newton's law tells me F equals ma.
Right.
In the y direction, is there anything moving? Is it moving up and down?
No.
So there's no acceleration in the y direction.
Then the second thing is I get why it's happening, but
Listen.
how can
Because the arrow is indicating the negative or positive portion. That's why the FBD is important. This arrow pointing left is what tells me to make that negative.
Okay, but when you solve for, you say, okay, yeah, it's time for the negative.
Once you've plugged this stuff in, the rest is just algebra. If you have a negative sign, you have to divide by that negative to make it positive. So it depends on the problem itself. It changes though, depending on the problem. In the y direction, what's acting?
FN.
Fn is acting.
Positive. So it's minus.
What's acting down? Fg. I was going to write it as mg, but I don't want to jump the gun.
And then minus FP.
Shh. Guys, you need to listen more. Stop talking. So acting up is Fn. Acting down is the weight of the object and part of the push or pull or whatever. Again, this person that's pulling on a rope over their shoulder at an angle, they're pulling down, but they're also pulling to the right. Since they're pulling, again, it'd be like me attaching a rope to this and being down here and pulling, okay? I'd be pulling down and to the right. Since the person is pulling down and to the right, FPY is going to be negative in this case. FG is acting down, it's negative. Fn is what's pushing back up. It's positive. Okay? Kian, you sure?
Yeah.
All right.
So when you do it like this, you're just, there's no equation. You're just adding up all of the forces.
Every problem is this way. Every problem. Now we can start substituting in what we know, Peter. But at this point, you're summing the forces. That's why you call it sum of the forces equals MA. Not sum as in SOME, but SUM. Sum. Okay? The sum, that's the symbol. Johnny.
Why is it easier to pull downwards at an angle and say just straight?
It's not.
So why do they do that?
It just depends on where it's attached to the body. If I'm shorter than the object I'm pulling, it's going to be at an angle, isn't it?
So they don't need to pull the chart from the top?
No. I think it knows it might be perfectly horizontal. The ideal situation would be horizontal. Yeah. The best way to move an object horizontally is by pulling all horizontally. I was just saying hypothetically. Okay? All right, our goal is to find out mu. Here's mu. Remember, this is where you start getting equations now. Or you had equations, but equations that you're familiar with. Peter, stop. Guys, stop. Listen, because you're going to ask this question. It's answering your question too. So you plug in mu Fn for FFK. And Andrew, answering your question, there's still a negative here, absolutely. So when you want to get mu at the end, you're going to have to divide by negative Fn to get rid of it. Again, to get mu at the end of this problem, to get mu by itself, you're going to divide by Fn, but you're also going to divide by that negative sign to get mu by itself. Fpx, since I'm pulling, okay, is really Fp cosine theta.
All right.
You're confusing it with your inclined planes. They're different things.
That'll get you.
Next,
Don't interrupt. Just
in the y direction, we have Fn. Fg is really just mg. Fpy is Fp sine of theta. And that equals 0. Now the only way we can get mu in this problem is by plugging in for Fn right here. We know this, we know this, we know this, and we know this. We know all this information right here. But we don't know Fn. That's the only thing we don't know. So we solve for Fn over here. I know I see your hands. Solve for Fn by adding these two things and then plug in for Fn right here. That's what Fn is on the right. Take that entire expression and plug it in for Fn on the left. And you get one equation as a result. The resulting equation looks like this. And by the way, at this point in time, if you would like to, you could plug in numbers and get a number for Fn over here. You could always do that if that helps you. Okay, that's the generic equation you're going to get when you take this and plug it in right there. So to solve from UK, if you were trying to solve this entire thing from UK, I would subtract FP cosine theta first. Leaving everything alone with mu. And then simply divide by the coefficient in front of mu. Remembering that to get mu by itself, yeah, you're going to have this max minus fp cosine theta, but you got to divide by negative mg plus fp sine theta. Okay, so again, let me explain. I know you got to go. You're dividing by this to get rid of it, but you also have to divide by a negative 1. So divide by this as a negative. That's how you get rid of that negative there.
Do you have the final answer?
No, I didn't do the math. Just plug in your numbers, you get an answer.